Morning, everyone. How y'all doing? Any questions, comments, concerns, etc. before we get started today? Alright. Please let me know any that you have at any time. For today, I'm going to continue on in chapter 6. On Monday, we continued looking at momentum in collisions and also defined impulse just as the change in momentum of an object. Usually if two objects are colliding with each other, they will have equal and opposite impulses, because if one of them loses momentum, the other has to gain the same amount and vice versa. Today we are going to, we've had lab this week, then this will sound familiar. Today we are mostly going to be looking at how kinetic energy also factors into collisions and look at two different types of collisions. But first, to summarize the things from last time, I'm gonna give you guys an example to work on your own for just a couple of minutes, and we'll see how everyone does. Here we're going to apply momentum in collisions to baseball. Babe Ruth is going to strike a fastball and knock it very fast in the opposite direction. The ball has a mass of 145 grams and is initially being thrown forwards at 44.7 meters per second. Babe Ruth is going to strike it with a bat and knock it backwards at 69.4 meters per second. I would like you to tell me the impulse of the ball and also how much force was applied to the ball to make this happen while the ball and the bat were in contact for 0.71 milliseconds. Put this one over, think about it for a couple of minutes, either on your own or with your classmates, Gesundheit, and we will check the answer. So, what do you guys think? conclusions as to the impulse yet? All right, well, definition of impulse is change in momentum. And since we know the mass of the ball and both its initial and final velocity, we can figure out impulse by considering how much its momentum is going to change. For all the different ways of writing impulse, I have settled on impulse equals mass times change in velocity. What number should we put in for the mass of the ball? 0.145, very good. That's because 145 grams is not in the unit we want, so that is the correct number of kilograms. Next, what should we put in for change in velocity?
69.4 minus 44.7.
Very almost. Now, that is the final velocity and the initial velocity, and delta anything is always final minus initial, so they are in the correct positions. However, there's something important to note here. The ball turns around, right? That tends to be the main point of baseball. The ball is launched towards the batter strikes it, and now it's heading back in the opposite direction towards the outfield. Which means that those two velocities point in opposite directions, and we need to account for that somehow. If you just do this, which would be plugging into positive numbers, therefore making them the same direction, you'd get a change in velocity of about 25 meters per second, which doesn't paint the clearest picture. Instead, what's happening here is the ball's initially moving at about 45 in one direction, the bat stops it and then sends it back opposite. So it drops from 44.7 to 0 and then to 69.4 in the opposite direction. So this thing has a very big change in velocity. So instead of 25, it's actually 115 approximately. And the way that we find that is that these two numbers need to be opposite directions before we plug them in, which you can accomplish just by putting a negative sign on the 69.4. Since delta anything is always final minus initial, this would be negative 69.4 minus positive 44.7. And that would give us negative 115 and something. You could accomplish the same effect by making the other one negative. In that case, it'd be positive 69.4 minus negative 44.7, which would still add them together. You just get a positive answer instead. Anyway, I believe if I do keep the negative signs like this, that would make the impulse negative 16.5445. Is that correct? What would the units on that be? Impulse has the same unit as momentum, since impulse is just change in momentum. So what's the unit for momentum? Very good. And this is, again, a far bigger answer than if you didn't make these two have opposite signs, because this paints the more complete picture. The bat has to hit the ball hard enough to completely turn it around.
Doesn't it have to be like 100 something?
Say again?
Like the impulse, like am I doing the math wrong? Or, because you said 25 was too small, so then why would it be negative 16?
Oh, sorry. The change in velocity would not be 25. 25 is too small for the change in velocity. That's what I meant.
Oh, okay.
Rewind.
Oh, it was the multiplication, sorry.
Right. If you didn't give these opposite signs, you'd get a change in velocity of about 25.
Okay.
In that case, you'd be doing 25 times this tiny number and getting a really small answer.
Okay.
What I'm recommending is the two velocities point in opposite directions, they need opposite signs. That makes the delta V about 115. 115 times this is where the negative 16.5 comes from.
Okay, I see it now. Sorry, I just missed the multiplication.
It's okay. I was having a real off day in my previous lecture. It's just one of those days, maybe. So that's the impulse of the ball, which is actually pretty substantial. And we're going to prove that by finding out how much force the bat actually struck the ball with. Because the bat was able to do this much of an impulse in less than 1,000th of a second. Collisions do not tend to last very long. And conveniently, one of the other formulas for impulse, J equals force times time, is perfect for figuring out the force applied for a certain amount of time. So we're going to take the impulse we just found. You are allowed to round your answers. That impulse is going to be equal to the applied force from the bat times the time the force was applied. What number should we put here?
0.0007.
Very good. Because we want seconds, and that tiny number is milliseconds, so it gets even smaller. Collisions do not last a very long amount of time. So we're going to end up dividing 16.5, etc. by 0.00071, and that's going to give us a pretty big answer. I'm going to round this a little bit. Approximately 23,300 newtons. As long as your answer is around there, then you're fine. Yes? Yes, it would, thank you. If the impulse is negative, then the force is negative, but that just means direction. If the ball's final velocity points negative, that's just, the negative direction. Bless you. The impulse pointed in that direction, and so too does the force from the bat. So that all tracks, that all makes sense. And you could very likely also get positive answers if you just decide the direction the ball is being struck in is positive and it was initially moving negative. So it's just kind of frame of reference. And for scale, that is about 23 times what I weigh. So that is a lot of force from a baseball bat. It's about 5,000 pounds of force. Now, as crazy as sports medicine numbers tend to get, note that that is not this man's punching strength. He cannot do that with his bare hands. This is with the assistance of a baseball bat. It turns out most sports that have bats or similar tools, you're really just using it as a lever to weaponize torque and increase your force output. So this guy could not lift 5,000 pounds, but he can hit something with 5,000 pounds with the assistance of a baseball bat. We're actually going to talk about torque next week or week after next. Turns out most sports, as long as they involve, a swinging implement, you're just weaponizing torque. Actually, most tools do that too. So, questions, comments, etc. Zoom tag. All right. Feel good with impulse? All right. So, we're going to continue looking at collisions and how momentum works in collisions, but it's time to talk about the different types of collisions. Because there is more than one, kind of like how there's more than one type of friction. Now, momentum is always going to be conserved no matter what. We've talked about how momentum only has one form. There's only one type of momentum. So it's always conserved. It's pretty easy to track for that reason. Total momentum initial is always going to equal total momentum final. The weird part when we start talking about different types of collisions actually begins to manifest itself when you start considering energy alongside momentum. Because if something has momentum, rho equals mass times velocity, it's also going to have kinetic energy at the same time, right? Because if your mass isn't zero and your velocity isn't zero, this formula will give you a non-zero amount of momentum, and likewise, the same mass and the same velocity would give you a non-zero amount of kinetic energy. So all the collisions that we've been doing using momentum, there is also kinetic energy involved simultaneously. Every collision involving momentum, there is also kinetic energy involved in all the moving objects, and that kinetic energy is also going to swap around where it is, what object has it, but also what form it's in. Because unlike momentum, energy has loads of forms that it can take. And the different types of collisions become a little more apparent when you consider what happens to kinetic energy in those collisions. There are two main types of collisions, and momentum works the same in both, because momentum is always conserved and there's no other form it can take. But the two types of collisions are elastic collisions, where objects tend to bounce off from each other and maintain more of their kinetic energy level, and inelastic, where objects do not bounce off of each other. They tend to stick together as a result of inelastic collisions, actually. They don't bounce around, they tend to be more controlled, less chaotic. And in those types of collisions, kinetic energy is not conserved, only momentum is. Now, to demonstrate that, I actually want us to backtrack a little bit. Do you remember the arrow in the log from Friday, I think? We're going to look back at this one. Previously, we discussed it through the lens of conservation of momentum. We noted how as the arrow approaches the log, the arrow has all the momentum, and then after impact, the arrow is going to share its momentum with the log. Each object will have a certain amount of momentum that adds up to the same total as initial, and we figured out the final velocity of the combo arrow log object. We are going to look at the same collision using the same change in velocity that we already found, but try to figure out what's happening to the kinetic energy instead of the momentum. The arrow starts at 25 meters per second, the log starts at rest. From your notes, please remind me the final speed that we found for these united objects. Thank you. 0.05 meters per second. Now we found that with momentum. That's good, that's all still true. Now, what I want to demonstrate is looking at the kinetic energy instead. Because if there's momentum, there must also be kinetic energy. And we're going to figure out the total amount of kinetic energy, both initial and final, to see if it's the same on both sides. Because unlike momentum, it's not a guarantee that all of the energy here stays kinetic. So, the initial side, which of these two objects has kinetic energy? Someone mouthed it. The arrow. The arrow is the one that's moving, right? So, like on the momentum version, Ke arrow initial plus Ke log initial. The arrow is going to have kinetic energy. The log's current velocity is 0, so it's not going to have any. Meanwhile, on the final side, after they collide, they will both be moving. Therefore, they will each have some amount of kinetic energy afterwards. So initially, KE arrow, 1/2 times the arrow's mass times the arrow's starting velocity, plus, same for the log. I keep wanting to make the log's mass 25, but that is wrong. Log's initial velocity is 0, so it doesn't have any KE to start with. Afterwards, arrow's mass didn't change, but its velocity did. So instead of 25 meters per second, its final is 0.05 meters per second, a very big change. And log is also moving at the same speed, so its final speed is also 0.05. So now let's figure out how much energy exists on each side of this equation. 5 times 0.01 times 25 squared. Oh, nuts. I keep wanting to write 25 for the log's mass, but it's only 5. I apologize. The log's mass is 5 kilograms. My mistake. Whoops. So, oh, nuts. I feel like I'm really off my game today. I keep making mistakes on my calculator and in my writing. I caught a few of them this time, but last lecture, students were just pointing things out to me the entire time. Feeling very self-conscious about it, if I'm being honest. Okay. The arrow's initial energy level, please let me know if you disagree, is 3.125 joules. The log has no initial energy level, so this is just the entire left side. Kind of like with the momentum, the arrow is bringing all the energy into the interaction. On the final side, both objects now have a very tiny final velocity, so they should each have a relatively small amount of kinetic energy after the fact. The arrow's final kinetic energy is 0.0000125 joules, barely any. And the log is not actually much better at 0.00625. So the initial is an entire 3.125, and the sum of the final side 0.0062625 joules. Are those two sides equal? No. There's no secret there. There's no trick. There's no way they would end up being equal. The thing we're trying to prove here is that the kinetic energy was not conserved in this interaction. The momentum was, but the kinetic energy is not. We lost like 99.5% of the kinetic energy on impact. Now, was that energy destroyed? Converted into other forms, likely heat. So it's not gone, it's just not kinetic anymore, meaning we can't really see it. It exists, bless you. It exists, it's just not accounted for here if we're only looking at kinetic energy. This is a textbook inelastic collision. I'm being very specific with the in part because I want to make it clear I'm saying inelastic, not an elastic. So this is an inelastic collision. These types of collisions, kinetic energy is not conserved, like what happened here. It's not conserved in the kinetic state. The objects tend to stick together, and the collisions tend to be very low impact, low velocity, not super chaotic. Which describes what happened here pretty closely. The arrow is just going to stick into the log, they don't bounce off from each other, and they have a very low energy final velocity. You might not even see it budge at first. So all that energy just kind of goes somewhere. And in this specific case, it would likely just be lost to friction as the arrowhead enters the wood of the log. The wood exerts a force back on the arrow as the arrow embeds itself a distance inside of the log. So that force of friction times that distance. Friction does work to take kinetic energy away from the arrow. Meanwhile, the log only gains a teeny tiny amount of kinetic energy while that happens. So again, this is the inelastic type of collision. And these tend to be pretty common. Most collisions are kind of designed to be inelastic because they are boring, basically, because boring means safe. Elastic collisions you usually have to go out of your way to cause, like building an object specifically so that it rebounds with elasticity. I've been throwing this at the wall all week as a demonstration, so noise ahead. Elastic collisions, there has to be an elastic object that can store its kinetic energy and then release it again. But these things aren't elastic, meaning that as the wood deforms, it just stays that way. It doesn't spring back to return the energy to center. This is how most real-life collisions work, again, by design. Because even though it's boring, it's safe. And for that reason, car crashes are designed to work like this. Car bumpers are made out of inelastic materials, so that like how the wood is going to deform and the arrow is going to embed itself in the wood, car bumpers are designed to do that too. When car crashes happen, the bumpers are designed to be crushed and then stay that way. Because if they were rubber and bounced back, they would throw the colliding car backwards and your own car would spring away from that interaction, likely throwing you into oncoming traffic and giving you whiplash before you even then hit anything else. So inelastic collisions are boring. Kinetic energy is not maintained in the kinetic state, as we saw here. Like most of it's gone. And the objects tend to stick together as a result, seen here by the fact that they shared the same final velocity. So most of the examples we've already done are inelastic in nature. Which means now we need to look at an elastic one to compare. Now I did just say that all car crashes are designed to be inelastic, correct? To kind of demonstrate the most extreme case of why that is, we're going to do a car crash as if it were an elastic collision, just to see what happens. So we're going to take two cars and literally just throw them at each other. They're self-driving, so I picked two self-driving talking cars from fiction. We have a sports car, Kit from Knight Rider, and a big talking semi-truck, Nemesis Prime from Transformers. That's Optimus's evil twin. And they're just going to drive straight at each other. So, initially, the two cars are going to head towards each other. They will have the same magnitude to their velocity, but opposite directions. I'm drawing the sports car first, so it's going to be moving at 45 meters per second forward, and its mass is 400 kilograms. Directly opposite that, we're going to have the semi-truck. And its mass is 2,000 kilograms. So, same speed, but opposite direction, head-on crash between two vehicles of very different mass. Before we even do any math, or before I even draw the afterstate, what do you think's gonna happen here?
The poor small car. It's gonna get smushed.
Poor small car is gonna get smushed. Yes, absolutely. Now, realistically, if these were real cars designed to crash inelastically, what would likely happen is that the sports car would, all cars are designed with a crumple zone, which is to say part of the car is designed to crumple so that the collision is inelastic and things don't bounce off from each other. So realistically, the sports car would just pancake against the semi-truck and everything would just kind of hopefully roll to a stop. But we're going to treat this as elastic just to show an extreme version of why we don't do that. Elastically, these things are probably going to spring off from each other at very high speeds. One of these two is likely going to completely turn around. Guess which one? Basically, you know what? It's actually going to look a lot like when any tiny object is thrown at a large object, it's going to get thrown backwards. Ow, sorry. Now, the problem with that is we can't guarantee yet what direction either of these vehicles is going to be moving in. We don't know for a fact that the sports car is going to turn around. And we also don't know a number for either of their final speeds yet. We have to find both of them. Because the thing with elastic collisions is they tend to be very chaotic. Things bounce away from each other. And since the objects don't stick together, we cannot assume they have the same final velocity. If this was inelastic and the vehicles stuck together like they're supposed to, they'd have the same VF. And we could treat this like we did the log question where it was just one VF in two places. But here, we can't guarantee that. So we have to treat them as if they have two separate, unknown final velocities. We'll get to why that's problematic in a moment. To start with, though, let's continue analyzing the momentum of the situation, as we've been doing. Because momentum's always conserved. We can always trust momentum to tell us something about a collision, no matter what type of collision it's going to be, elastic or inelastic. So, total momentum initial equals total momentum final. Initially, both vehicles do have momentum. So, momentum initial car plus momentum initial truck should equal momentum final car plus momentum final truck. So good so far? Now, we actually know everything we need on the initial side, which is nice. We've got both vehicles' masses and both of their initial velocities. Main thing to note, though, is that both velocity and momentum are vectors. So we need to care about and indicate that these two point in opposite directions. I'm going to make the car positive because I drew its arrow pointing to the right. So momentum initial car is going to be the mass of the car times the car's initial speed. Plus, for the truck, its mass times its negative pointing initial speed. This does actually mean that the total initial momentum will be a negative number. Negative not meaning like anti-momentum, it just means it points backwards. It points in the negative leftward direction. Before even looking at the right side, I'm actually just going to figure out what the left side equals. I believe 400 times 45 is 18,000. And bless you, 2,000 times negative 45 is negative 90,000, which should give us a lump sum on the initial side of negative 72,000 units of momentum. So the total momentum of the system does point left. Again, that doesn't mean anti, it just means leftward, which is very bad news for the sports car. So that's the left side done. We've gotten the initial total, which is good. So now we need to look at the final side to compare it to. On the final side, the vehicles have the same masses. Usually an object's mass doesn't change on the fly. If it did, it's probably because it got broken into lots of separate pieces. But we're just gonna keep their masses the same. The problem is that their final velocities are not the same, or not guaranteed to be the same VF like they were with the arrow in the law. So we have, until we know for certain that they're the same, we have to treat them as separate, since we are not guaranteed that the vehicles stick together like they should be if they were built smartly. And that means we have one equation with two unknowns in it. Guess what happens next? It's everyone's favorite part. It's the same thing that always happens when you have two unknowns in a single equation. We need a second equation with the same two unknowns in it, tragically. Now, thankfully, I'm going to tell you what sorts of equations you can use in this scenario. You don't have to invent one on the fly. These are your three starting points for collision questions. We've been using this first one, conservation of momentum, because this one always works. This one is always true for any type of collision. But if we are specifically treating this example as an elastic collision, again, to demonstrate why cars don't do that, this is also true. Total kinetic energy initial equals total kinetic energy final, and we can use this as a second starting point. It would look a lot like the conservation of momentum, just using, the KE formula several times instead of the momentum formula several times. And frankly, if you have the same pieces of information, the same, these two things will get you where you want to go, because they both of the formulas for momentum and kinetic energy have mass and velocity. So it's just a second equation with literally the same two unknowns in it. It's just a little frustrating since that KE formula has the extra 1/2 in it, but the really frustrating part is the squared. But we can use it as a second starting point, as long as it's an elastic collision. If it's inelastic, this is not true, and you can't use it. And I will tell you in a question if something is elastic or inelastic or not. You will have that information. So you don't have to necessarily just look at what's described to you and guess. I will tell you elastic or inelastic. If it's inelastic, this is your only option, and frankly it's a good option, because if it's inelastic, the objects tend to stick together and have the same final speed anyway, which means it would work just like the arrow question, the same VF. But if it's elastic, you can't usually guarantee the same final speed, and you'll likely need a second equation, and this one does work for that purpose. I'm going to try to simplify it a little bit to save space on your notes. The initial, no, I can't, just hold on, there's another. Sorry, I take that back. Initial kinetic energy, both objects have it. Interestingly though, the negatives on the truck's velocity are actually going to go away. since the velocity is squared. And that's because energy isn't a vector. Energy is a scalar. So any negative sign that we have here is just going to vanish. Since the energy doesn't really care what direction you're moving in, it just wants you to move. So that's our initial side. Two masses, their initial velocities, but using the kinetic energy formula instead. That's going to give us a lot of energy, like very big numbers. .5, 400, 45 squared. Just the sports car alone is 405,000 joules. And the truck, again, note that the negative is going to cancel out. Has over 2 million joules. Because it takes a lot of energy to make very heavy things go fast. So adding these up, the entire left side turns into an initial energy total of 2,430,000 joules. So that's how much energy is brought into the interaction by both vehicles. And in an elastic collision, this will remain constant. They're just going to swap who has more of the energy. So on the final side, 1/2 times the same mass times the car's unknown final velocity plus 1/2 times 2,000 times the truck's unknown final velocity. Now those are both unknowns, so we can't really simplify those parts very much. What we can do though, 1/2 times 400 is 200, PF car squared. 1/2 times 1,000, 2,000 is 1,000, PF truck squared. Those two unknowns are different. We cannot combine them, unfortunately. However, we can at least, what I like to do, you're allowed to disagree, is technically we could distribute a 200 out of both of those just to get rid of it and have to stop writing it. And by distributing a 200 out, we could divide it under the other side just to make all the numbers smaller. So that's one option. It's one that I liked because then I don't have to write as many big numbers for the rest of the question. So that would look something like 200 times PF car squared plus 5 times VF truck squared. So we can just divide that 200 over to get rid of it and make the entire question smaller. So just factoring out 200 from the whole thing. Which would be 1,150 equals BF car squared plus 5 times BF truck squared. And that is our second equation with the same two unknowns. And at this point, what we would then need to do is take this, solve it for one of them, and plug it in over here. Does that look fun? No. As much fun as two equations, two unknowns already is, the problem with the kinetic energy version of this problem is that's squared on all the velocities. It means that in order to solve for one of those V's, Like say if we want to solve for VF car, we'd move this over and then we'd have to take the square root of the whole thing. So we'd be plugging a square root into the other one, and it's just kind of a pain. It works, but it's a pain, which I feel like is probably the tagline for physics in a lot of your heads, which is fair. Thankfully though, this would work, but it's not our only option. Because there's actually, I was about to say secretly, but it's not really a secret. There's a third choice for our starting equation. There's a third equation with the same two unknowns in it that we can use instead of this. Some very smart people took the previous two equations and pre-combined them for you into this. As long as it's two objects involved in a one-dimensional collision, which just means forward and backward in a single axis, V1 initial minus V2 initial will equal V2 final minus V1 final. It's a very handy relationship between the final initial velocities of two one-dimensionally colliding objects, as long as it's an elastic collision. So this is a totally valid second equation. We could use it to plug into the other one. It's just a pain because of the square, but it would work. However, this already has the squared worked out of it. So we could use this as our second equation instead. And since we're running out of time, I will just quickly demonstrate how that works. So this is our second equation with the same two unknowns in it. I'm now going to set up that third equation with the same two unknowns. V1 initial minus V2 initial equals V2 final minus V1 final. To use this equation, you just have to pick which object is 1 and which object is 2, and then make sure you keep straight which one goes in which position. It's not the same order each time. It's 1 minus 2 equals 2 minus 1. You don't want to get that backwards. If, just kind of keeping the ordering from before, car is 1 and truck is 2, that would be 45 minus negative 45 equals V F truck minus VF car. So I kept through, all the way through this, object 1 was car, object 2 was truck. And yes, they do intentionally switch positions on the right side. This can also be our second equation that has the same two unknowns in it. It's got VF truck and VF car. Those are the same two things we're missing over there. And this, numbers are smaller and there's no square. So using this, it's usually preferable to the kinetic energy version. This equation was developed using the kinetic energy version, and that's why it only works for a 1D elastic collision. That word is missing here. 1D elastic collision between two objects. So you can't use this for the arrow and the log that stuck together because that was an inelastic collision. This only works for elastic. These two are both elastic only. This one is specifically 1D elastic, but that's really the only type of collision we're going to do in here, if I'm being honest. Like, you can't have a 2D collision, and this one wouldn't work for that, but this will work for this class, as long as it's elastic. So any three of these work to analyze elastic collisions, and often, if you don't know either final speed, you're going to need to use at least two of them. Now, we're out of time, and I don't want to hold you up. How this would move forward from here is, this is our second equation, we solve for one of them, plug it into the other, and kind of give the game away. The truck is going to slow down to like 15 meters per second in the negative direction, and the car is going to change from 45 forward to 115 backward. The car loses this fight, and we'll prove that math next time. So bring these notes, don't lose your position, and also bring these notes to the lab, and let me know if you need them. On Friday, we'll finish this one up, close out chapter 6. I'm just trying to link this one. Please have a nice day.